we are going to plot the stress 3-point bending stress versus strain curve for the experiment for the flexural test what we have done for the glass fiber reinforced composite and pine wood. So we got the output, the force and position. Now we have shifted this position to absolute position to 0 because we have given a 12 Newton of preload. So we remove the data up to the 12 Newton. Okay. So what is the flexural stress or the bending stress? That is 3PL by 2BT square. So we are going to use the equal to 3 into P. P is the force into span length. Already I have explained the span length that we have took the 90. How we have took the 90? We already know the length by thickness ratio. We use the 16. The thickness is 5. So length is span length is the 90 mm divided by of twice into width. Width is the 13 mm into of thickness. Thickness is how much? Just I told you 5, but exactly it is 4.95 square. So like this we have got the stress at this position. Like this we got the stress at every position. Okay. Now we want the flexural strain also. Flexural strain, that is in mm by mm. Okay. So here are the two things are there. First thing is the values. There is, I have written the flexural stress in megapascal, the unit. You can see it here, 3PL. The force is in Newton, length is in millimeter, width is in millimeter, thickness are in millimeter. So Newton per millimeter square will come from here. That is equals to the megapascal. Okay. Similarly, we are going for the flexural strain, that is 6 into of thickness is 4.95 into of position. Sorry, I have written the here P in the formula, that is position. The position is this absolute positions divided by of span length ka square, that is 90 ka square. Like this we have plot the flexural strain. So I am just changing it here. I am just writing it into delta so that it will be easy to understand. Okay, so like this we have got the flexural stress versus strain. Similarly, we will go and plot for the case of the wood also, then we will plot it together. Okay, in the flexural stress we are going to use the same thing, that is 3 into P into L, the span length here also the 90 mm divided by of 2 width. Width is 13 mm into of thickness. Here the thickness was 4.9 ka square. We got the flexural stress at this position. We can get the flexural stress at each position. Now you can see that it is starting from 0. In this case it is not starting from the 0, but that you can see in the curve also. The flexural strain is equals to 6 times of thickness, that is thickness is 4.9 into of position, that is the 0 divided by of length ka square. The length square is 90 ka square. I can plot it for every position. Now I'm going to plot it. How? Insert graph. We got this graph. Now we are going select data. In select data, add GFRP, glass fiber reinforced in X. We are going for flexural strain. In the Y, we are going for the flexural stress. X is the flexural strain, Y is the flexural stress. Then we are going to add, we are going to use the pine wood. We are going for the X, that is a flexural strain, and Y is the flexural stress. Okay, we have gone, we have plotted. Let's see. Okay, access title and legend. We are expanding it. Okay, so this is the stresses. These are the strain, and you can see the comparison between the pine wood and GFRP. I don't want to plot it together, but okay, let's see the difference between the wood and a glass fiber reinforced polymers. So you can see the glass fiber reinforced polymer is having a flexural stress of 350 megapascal. 350 megapascal. And you can see it is approximately linear, and when it will reach at maximum it fails, and it is a brittle failure and it drops. You can see actually easily that it is a drop in the curve is there. So this drop, whenever this drop occurs, the UTM stops automatically. Okay, for a particular percentage drop, there is a procedure for specimen break. You can see the pine wood. If you are seeing the pine wood, you can see that it is going approximately 120 megapascal. 120 megapascal, or I can click it here. How much value it is showing? It is showing 115 megapascal. That is a maximum flexural stress, but you can see the curve is up to here, it is linear, after that it is non-linear, and there is a drop in the curve after reaching it 115. So this, if you have seen the experiment video, you will come to know that there is a breakage of wood was there, and the proper sound you have listened. Okay, so like this we can draw the stress strain curve. We can find the maximum values. Yes, we can find the maximum values, and AX maximum value for the stress for the case of glass fiber reinforced polymer, that is 356, and for the case of it hangs for a while, for the case of wood, we can see for the case of wood it is 118 megapascal. So if you want to say someone what you have learned today, that you know that the tensile the flexural strength of the glass fiber reinforced is approximately 3 times of the wood. Okay, that's why, because the wood and glass and carbon fiber all are the lightweight material. Okay, we are using this glass fiber, carbon fiber, because it is having the higher tensile strength and the flexural strength. Okay, friend.